Okay.
Okay, sir. Okay, sir.
Movement from outside. There's 1 or 2 minutes I'll be back. How many are here? So 1, 2, 6 only.
Sir,
Okay.
5.
We'll start. Uh, Today's what? 11. So where are we? We'll just check out. Okay, see what we have done till yesterday. So I want you to just explain you a little bit here, so that what is expected. So Rishabh and others. So see whatever I have written yesterday, I think it is correct only. So this I'll just remove these question marks. This is correct only. Now you can
Yes, sir.
easily, right? Are you convinced? So if
Yes,
ur
sir.
is greater than 0, that means basically the velocity radial direction, it is positive. So that is basically you are saying that flow is actually moving away from the origin. So it's greater than 0 means less than 0 means, okay, how do you convince this ur? Ur is basically r radial direction, it is positive means basically next level. No, if you go a little further up, where is the particle next point of time where it moves, basically that's actually going towards away from the origin. So if it is less than 0, it is coming towards the origin. So similarly, U theta is basically, so this is your theta direction, theta cap, and this is your R direction, R cap direction. If you actually see perpendicular, right? So for this I'm not writing as X and Y. So this is an example for this circle. If you draw this tangent, the tangent, you see this is the direction is the way is flowing. For the vertex flow, this is your theta, and this is the perpendicular to this thing is your R. That is anyways, that is understood, right? So this is what. So as theta is if U theta component, this velocity in this direction is theta, means it's basically anti-clockwise. Okay, so this you can just use it, confirm it using your what is that one, vertex flow, point vertex flow that you have now, gamma by 2 pi times what is that, ln. On the x-axis, if you actually see it, the direction vector should be, the direction should be in the y direction. That means x direction, x component will be 0, u is 0 here, v is positive. That is how you verify whether it is actually u theta component is positive, means anti-clockwise. So the anti-clockwise means basically at here the u component, if you convert this into point on the x-axis, if you actually see the flow velocities, you comma positive y component, positive v, u is 0 and v is actually positive. So that's how you see that it is actually moving in the clockwise, anti-clockwise direction. So that is the case when u theta is positive. Fine, right?
Yes, sir.
When we looked at this flow also, you can do the same thing. So it's away from origin. This one is also another. Everything is away from the origin. I think this is away. This is coming from. This is coming towards origin. This one actually, if you come like this, no, from far away, it is coming towards the origin, and then somewhere here it's moving away from that. So both the direction, I think that's what you have to see. From here to here, it's coming towards origin, from positive y-axis to here, and this towards this, it is going away from this. Or you don't know, here may not be able to see, but anyway, so certain flows you can't simply decide based on u or u theta. That is the reason you have all why we have done this what is this curvilinear coordinates. Sometimes it is easy to see r theta, sometimes you see the Cartesian. Based on that, you decide the flow direction and you decide the flow streamlines. Okay, so that is the main purpose of this curvilinear or different coordinate system. You have the components of velocities. Okay, so psi of xy equal to 0 is actually gives you basically sometimes. That is also streamline. So what is streamline here? Xy equal to 0. So all these are actually xy axis is also streamline here, isn't it? Yes, because
Sir, sir,
yeah.
sir, I have doubts, sir. Like you said u theta greater than 0, there is anti-clockwise. Anti-clockwise, then sir, here u theta equal to minus 2a2 r sine 2 theta. Our theta belongs to from 0 to pi by 2. If you multiply
No,
it to,
don't look at that. Don't look at that way. Certain flows you may not be able to see.
okay,
Certain
sir.
flows you can easily see. So, for example, you have the vertex flow. Vertex flow. What is this theta cap? Is this theta cap component is only u theta, right?
Yes, sir.
So in this direction, this is your this thing. So at x, where did you take this tangent at x comma 0? At x comma 0, right? On the x-axis you have taken. So you convert this into usual Cartesian coordinate and see that only y component, that means v is less than 0 and u is equal to 0. Then that means this whatever you are doing. So positive means it is that, right? See, suppose you know what it is, right? This is equal to gamma divided by 2 pi. Gamma is positive. Gamma divided by 2 pi. What is that? Ln of x square plus y square, right? y equal to 0, you have taken 0. So this is like 2 into ln x, right?
Yes, sir.
So you have to convert this into polar coordinates. Okay, so I think I should not convert right away. So and do the mistake. So you first convert this u v u r u theta. Okay, whatever u r u theta. So what I have is phi, right? Phi is actually ln r. So that you convert this is that is going to be ln of x square plus y square. So what is the v? V is actually what is dou phi by dou x is actually your u. What is dou phi by dou x? 2 into x ln of x square plus y square, right? So, but this is the streamlines are perpendicular to this, no? So you actually want psi, not phi, isn't it? Hello?
Yes, sir. Yes, sir.
Or phi, you calculate phi, whether you got this phi as your LNR, I think that is psi as your LNR, right? So
Yes.
just look at carefully and decide. So for example, vertex flow, you know that is the simplest flow that you have. At this point, you look for what is the direction in Cartesian coordinates. If where u component is 0 or v component is positive, that means the direction of the flow is in this one. That means it's anti-clockwise, right? That is how you decide first. So in general, that is the case. So certain streamlines you may not be able to see exactly, even with u or u theta. In that case, you have to see exactly ux, sometimes ux, ui, sometimes u or u theta. Based on that, you decide the flow direction. That you needs to be smartly do it. If you actually see psi of xy is x into y. So xy equal to 0 is actually a streamline. So that shows that x and y axis are streamlines. But they are also stationary points. All the points are stationary points. That means it's basically they are all stationary points. Okay, these are all stationary points. And you have seen, so in the all the n greater than or equal to 3, you have seen that they are confined to, because psi equal to 0, psi equal to 0, these are the streamlines. Those are, you don't, whatever flow inside this won't cross going out. So psi equal to 0 means basically it will give you some kind of, that gives the barrier to the, so the this side of this psi less than 0, psi greater than 0, so you will have, that is the stagnation. That is what is the boundary for the flow. So you have confined to this. Okay, so these are wedge flows. Okay, so these are wedge flows confined to between the angles. That's what you have seen. Now we try to make a combination of them. So you consider uniform and source. If you consider uniform and source, yeah, this is actually phi only, no? Source is actually phi only. Yeah, source is phi. Source has phi has LNR. Otherwise, that is actually psi. For vertex, it is psi. Okay, psi is actually involving a log r. So this combination, if you take, then what did you see? This flow is basically gives you, what is that you give you? Stagnation points you find out, and finally you got the streamlines. This is the special case when you allow the uniform flow and a source. Basically, it gives you Rankine half body. Okay, so that's what you have seen. So you look at the stationary point, and then through which there is a streamline that actually divides the flow inside and outside. So whatever is inside is basically Rankine half body flow. Okay, so inside that is also called Rankine, but we will see. Okay, is actually Rankine half body or something. Okay, so half body flow. This normally this is what you say. Okay, for this flow, that's what you are saying. So if you combine them, so you also put the source and sink together, and that becomes Rankine oval. So this is the Rankine in fluid mechanics. This is called Rankine oval. Okay, so where we actually have separatedly, you have source and sink and a uniform flow. Okay, so you have a uniform flow along with source and sink putting next to each other, but you didn't make them very close to, you didn't bring them together. Okay, so then you have a oval, but as epsilon goes to 0, this oval becomes this your circle. So that is what. So once you allow epsilon goes to 0, source and sink putting together will give you doublet. The doublet we have already seen that this is going satisfied. That is what is actually UR on the circular cylinder. U theta may be varying little bit here, so it's like a flow parallel. Okay, slip will be there here because this is a potential flow. You have a slip. You have the U theta is this one. But there are two stagnation point. Those are not only U are equal to theta, U theta is also equal to 0. So if you put that one, that is the stagnation point where the velocity, both the velocity components are 0. That gives you that theta 0 and theta pi both are stagnation points, and correspondingly you want to see whether passing through that one, that gives you your whether this circular cylinder itself may be a stream point of your psi of r theta. Psi of r theta is what you already seen now. Psi of r theta. What is psi of r theta in this case? Psi we have seen, right? What is psi?
Uh,
Did we write the psi? Psi we have not written, right? What is the stream function in this case? Yeah, you already have psi here, right? U r sin theta. U r sin theta plus
Q theta by 2 pi.
that is for something else. That is for this flow. That is for Rankine half body. Now you have a epsilon. That is for now you have this is for this flow. Now what you have is this epsilon, the doublet thing you need. Doublet thing, you try to calculate what is your psi. So that that psi, if you differentiate, and you will see that whether you are getting the same UR and U theta. For that, and then put this passing through that one. So make it equal to psi at 0. Psi at the stagnation point. That is what is the calculated these points. For example, a comma 0 or a comma pi. At this point, what is your psi? That you make it as psi of x0 equal to psi of a0. Okay, a0 or a pi. So this is your, if this gives you as a circle, this is the curve that gives you a circle. Basically, that whatever the boundary of that cylinder is your streamline. Okay, so this you verify. Again, I'm asking you to do it as an exercise. So that is how you will learn. Okay, sometimes maybe solid cylinder, it need not be, right? So it need not be your streamline. Sometimes they all may be stagnation points. So obviously it will be streamline. If it is not all stagnation points, obviously it has to be streamline. Streamlines are very close to the solid surface, right? You can always bring them close to that. Basically, that solid surface itself will become, that circle will become your streamline. Okay, so that's how you have done the simplest one with the doublet. So what is the next course of thing is basically you can main idea is to calculate what is your uh, I'm going to close using based on the solutions of the Laplace equation. Potential flows involving only phi. I derived this flow, right? Flow past the cylinder. And now we have these stagnation points at which you will have the forces. If you actually see this one, see what you calculated is only phi, right? So phi you calculated with these boundary conditions only. The momentum conservation is actually equivalent to Bernoulli equation. What is the Bernoulli equation now involving? That is your phi and pressure is connected through your Bernoulli equation, isn't it?
Yes, sir.
So that pressure and so we will write that Bernoulli equation now. So what is the Bernoulli equation? The Bernoulli equation is so what are you going to do? Bernoulli equation is basically gives you right. Of course, what you are dealing with is only steady flow, right? These are all steady flows. That's why there is dou phi by dou t. I am not writing. So p by rho plus g times z plus half u square equal to constant, right? Isn't it?
Yes, sir.
But you are looking at the z cross section only, right? So that means you take any 2 points, right? So you take any 2 points, pressure at that point by rho plus this same g level, okay, plus half, let us say u1, okay, at that point the velocity is u1 equal to same, it should be constant, no, it is same. So some other point. Let us call this some other point P2, at which the pressure is P2, and you divide by rho. This will be, we are at the same level because Z is, we are cross section of Z at certain Z only, both sides are same Z. And here this will be half. Let us say here you have a U2. U2 is the velocity of the fluid there. So these two are same. Okay. So now what I do is I will try to consider P1, those 2 points. So what are those 2 points you consider? Okay. So okay, let's put first now like this: P1 minus P2 divided by rho equal to half U2 square minus U1 square. Okay. So I will take P1. P1 being, let P1 be, P1 is the pressure on the surface of this cylinder. Okay. That is at R equal to A. That is at pressure at R equal to A. That is pressure at R equal to A. That is on the surface. Okay. That you call it. And let's take P2 as infinity. Okay. So is the P infinity, that is pressure away from R equal to A. That is R goes to infinity. That's what we are calling. Okay. So in this case, what is your U1? What is your U1 on the surface? What is your U1?
U1 equal to U2, sir.
U1 is
On
actually UR, right?
yes,
What
sir.
is what is U? U means what? U is
Velocity.
basically, U is basically, it's a vector here, right? So these are all vectors. I should put it as vectors, right? So what is U1, for example? So U1 is basically the modulus of this, right? So modulus of this is equal to square root of the magnitude of U1 equal to, so UR square. So UR square, UR U theta components, no? So UR square plus U theta square. So if you write this one, UR is anyway 0. This is anyway 0 on S. All right. On R equal to A. At R equal to A, if you ask, that is what you have chosen, no? As your one. Okay. So U1 will be, so magnitude will be simply modulus of U theta. What is that one? What is your U theta? What is your U theta? Just calculate U theta. 2U sin theta, no? Modulus of this is this one. 2U sin theta. So you put it as 2U sin theta. So modulus, that is going to be 2U sin theta. Okay. And what is your U2? U2 modulus will be at simply only U, right? That's only U. At infinity, no? Away from infinity, you have only uniform flow, that is U. U or cos theta. So you take the modulus, that is 0, right? That modulus is basically, you know, that is only one-dimensional flow. So that's what you have. So this implies, so if you actually write that P1 minus P2 divided by this thing, if you calculate, what is that you are gaining? That is your PS minus P infinity divided by rho equal to half U2. U2 is U square, that is U square minus, what do you have? 4U square sin square theta.
Yes, sir.
So this is like, you know, this is why we define like this, is basically to define your pressure coefficient. You can define something called pressure coefficient. It's basically, you know, just a relation between P and your pressure. So based on this pressure coefficient, you can conclude certain things. Okay. So pressure coefficient I'm defining as Cp. This is the, by definition, is like Ps by P infinity by rho. Rho, this half U square, you bring it down. Okay. So you bring it down here. So you bring it this side. So you'll have a denominator half rho u square. Half u square, you bring it down. So this, so that this becomes 1 minus 4 sine square theta. So this is your pressure coefficient. So if you draw this pressure coefficient, you can easily see that between 0 to pi on top of the sphere is what you have sphere, no? So if you say 0 to, this is theta equal to 0, this is theta equal to pi. And when you come here this side, this is theta pi to 2 pi, right? 0 or theta is 2 pi, or theta is pi to 2 pi, or 0 to pi. Above 0 to pi, 0 to pi, if you do, this is actually goes something like, so what happens at x equals 0? Sine 0 is 0, so it is 1. Okay, that is 1. What happens here at pi by 2? Pi by 2, it is minus 1, minus 3, right? So it slowly comes down, finally minus 3. This is at minus 3, and this is at 1. And then it goes back to, at pi, it finally goes back to 1, right? At pi also it is same, right? Sine square theta, no? So this is what you have. It is also symmetric. Basically, this tells you, this curve tells you that pressure is also symmetric. Okay? No, it's not pressure actually. This pressure coefficient, as you see, you go from here. So it is actually decreasing here. So you have a less pressure here. You will have a lowest pressure here, right? This pressure, and then it started decreasing. So the lowest pressure value is here, right? This is the lowest, right? Where this is at pi by 2. So you have pressure decreasing, and then lowest value, and pressure is increasing here. So what do you do? So where is this going to move? There is a pressure balance, right? That's how you calculate your forces. Okay. So there is a pressure, low pressure, pressure as you go from lower to easy. This is basically increasing. In this direction it is decreasing. In this direction it is increasing. Okay, from peak theta equal to pi by 2 to this one. So you don't worry about this one. This is some kind of physical way we are looking at it. But this just tell you that P and your pressure both are connected. So you see this is symmetric. Symmetrically distribution is there as a pressure. So what I'm trying to do here is that based on this decreasing and increasing, you can easily see. So now we will try to calculate the pressures, forces. Okay. So forces on the cylinder. So how do you calculate my force? So force is basically equal to, force is a vector, right? So that vector is basically integral over. So what is that you have? What is now you basically full cylinder you should have. That is your two-dimensional body over S. S is your cylinder, and you have this shear. Normal stresses. Okay, normal stresses. What do you call this? NN. Well, let's put this normal stresses. Okay, and it's this. This is your normal stress. Normal stress. Dot product with the normal unit normal. This is with ds, right? This is your ds, surface area, right? So this is equal to, what is that you already have? One normal stresses in for ideal fluid is only minus p, right? Minus p dot p n cap, right? It is simply p n cap. P n cap is not dot product, right? Yeah, this is the dot product. It's only perpendicular way. Both are perpendicular to the surface. That is why we simply get P n cap. So you know, right? P into n cap. Why P n cap? This is the pressure is basically scalar quantity. So how do you get this one? P n cap minus P n cap. We have done now when we derive these forces, surface forces acting on the fluid element. Just look back when we derive those equations. Okay. So this is your ds. Now what you have is only cross sectional area. So your S is basically only on this perimeter, right? This is a perimeter. So over the perimeter, what happens? ds, the small ds is basically perimeter is this is simply, this is your theta, I mean d theta. This is your cylinder of radius A. So A into d theta is your ds. Is it okay? Yes.
Yes, sir.
And then okay. And then what is that P normal? So then what you should have is this is the force, and this is actually, once you reduce it over cross sectional area, so this is per unit length, right? Unit length of the cylinder, isn't it? So that z direction, z to z plus dz will be 1, and over the perimeter you are integrating. That's what is the meaning of per unit. Force per unit length of the cylinder is basically, now you are integrating over theta. Theta is over the perimeter 0 to 2 pi. P is the pressure. So now what is this Pn? Pn will give me, so what is the normal here? Cos theta sin theta, right? So what is this normal? This vector is what? Cos theta sin theta, because in polar coordinates, isn't it?
Yes, sir.
So for example, see, this is your x-axis, y-axis, basically anything. Now this is your normal, so this is your theta. So this is your cos theta sin theta. Okay, so that is your normal. So you will have a P cos theta instead of cos theta, dot product, no? Uh, y cos theta, sin theta, what will happen? Sin theta is also there, no? Both are there. Cos theta, sin theta, both you have to put it. This is normal. It's normal, both you put it. So PA, this P, okay, let me write neatly. This is the pressure. Normal is cos theta sin theta, A d theta. So you both will have F x component of per unit length of the cylinder. Okay, x component equal to minus integral 0 to 2 pi P cos theta, A P cos theta. So A comes out, A P cos theta d theta. Similarly, Fy per unit length of the cylinder. This will be minus, again, one more. These are the force calculations that you made. AP sin theta d theta. See that these are the force components, okay? Per unit length, this is what you have done. Okay, so whatever that x component, you call this drag. This is your lift force. Y component is basically your lift force. So basically, you're concentrating on the full circular cylinder. What is the x component of that force? Y component, effective force per unit length. If you call this, that basically gives you overall effect. So whether you have the net, this is basically net force. Okay. So per unit length of this, basically net force basically. So whatever you're doing, this is basically net force, right? This is basically net force, right?
Yes, sir.
So that net force, x component is that, y component is the x component, you call it drag, and y component you call it lift force. These are the drag force, lift force. Okay. So this is not just for the cylinder. You can also this is for any general body also. These are the calculations that you will learn from this Blasius theorem. There's something called Blasius theorem that will work. Okay. So you can now calculate for your particular thing what exactly those calculations. So how do you calculate your this one? Yeah. So how do you calculate your for your problem? Calculation of fx per flow past circular cylinder. Whatever we have done now, uniform flow, you allow and doublet, that is basically circular flow. So in this case, if you calculate, what is your Fx equal to minus A comes out, which is constant 0 to 2 pi. And what is that is your PS now. So what is your PS? PS is the pressure on the cylinder, right? On the cylinder, right? So this is actually PS cos theta d theta. You know what is your PS? You know, right? So what is your PS?
P1 sir, that
Whatever you have formula, no, I'm just writing directly minus A integral 0 to 2 pi, and this is actually turns out to be P infinity. Okay, so what is P infinity? Also we got, no, we didn't get, right? P infinity as it is, yeah. So P infinity plus of rho u square, that is in the denominator you have, and then this is actually constant. Okay, so this is 1 minus 2 rho u square sin square theta. This, that is what is your PS cos theta d theta. Oh, I am writing here itself. Huh? So this, okay, I didn't make use of that lecture 25. Anyway, doesn't matter. So, okay, fine. So science data. So what is this component? So now can you explain what is this? This is anyway constant. This is just a constant. Constant cos theta integral 0 to theta is 0, right? Sin square,
2
sin
pi
square
sir.
theta cos theta. What is the integral?
Sin square theta cos theta.
Sin square theta cos theta, you write like 1 minus cos square theta into cos theta. That is cos theta minus cos cube theta. Okay. What is its value?
So we can use that one, so sin theta equal to x. Use the change of variable method, sir.
Yeah, you can do that. Then what is that you are getting?
This
What is its value? Can you just calculate and tell me? Yeah, sin theta equal to theta t square. Sin theta means sin 0 0 sin 0. That, so it's what is the t value? That's a problem, right? If you do that, what I'm saying is if you do, for example, sin theta equal to t, if you put it, because you're doing over 0 to 2 pi, what happens to your that one? That is 0, no?
so then zero to the value will be zero, sir. Then
0 anyway, finally. So or you just
yes.
calculate, try to look for the sin square theta, cos square, cos theta. This integral will be 0. Okay. So that integral is 0. So finally you get a 0 here. Okay. Just check it. So and similarly Fy. So this is your drag force. So drag is this much. This lift force is actually Fy. Here also you calculate like this, 0 to 2 pi Ps sin theta here. That's the only difference, right? So instead of P, you have PS. PS is same like here from that thing. So you have a same thing you have. So 0 to 2 pi. So you have P infinity plus half rho u square is a uniform velocity minus 2 P rho u square sin square theta sin theta d theta. So again, sin theta, first constant time sin theta is 0. And what about sin cube theta? Sin cube theta integral is what? What is sin cube theta?
Sir, I am calculating, sir.
That will also be 0. Why is this 0? How do you calculate that to be 0? You calculate and make sure that that is also 0. Okay. Since integral 0 to 2 pi sin cube theta dt theta. What is its value? So here also 0 to 2 pi sin square theta cos theta d theta is 0. These basic things you check. Okay. So what you have is basically is this one. So on the cylinder cross section, solid cylinder. So you basically have flow like this. Okay, this is a uniform flow away from the cylinder. On top, you have no pressure here, and the pressure is decreasing. So lowest pressure here, pressure is decreasing here. So that is why you expect, but there is a balance, right? So whatever is increasing, it is actually decreasing here and then increasing here. There is a balance, right? This side and this side above, right? So similarly from here to here. So if you actually see here and here, okay, so right side and left side are top to bottom. You actually see that pressure is basically, if you look at the pressure is also symmetric. And instead of seeing that, only velocities are also symmetric, right? So you see by looking at the stream function, velocities, the flow is symmetric. Flow is symmetric from top to bottom and from left to right. So that just tells you that the pressure is also similarly this thing. So, and you actually calculate it and you see that this drag and lift are zero. This is actually paradox for real fluids. For real fluids, because of flow separation here. Okay, there's some boundary layer taking place here. So because we are considering only that we have not considered now for real fluid means fluids with viscosity. Viscous fluids, we have not touched upon that. So you need to look at that momentum equation soon. Okay, once we finish this part, you will have flow separation. That is where the boundary layer theory takes place. And also you have because of the viscous fluids, there is something happens here. So there is a vorticity. Okay, so because of that there is a vortex. So there is because of these rotations here, smaller local rotations, because of this what viscous fluids, you have a lift force or drag force takes place. Okay, drag and lift force are not zero. So this is experimentally done, proved. Okay, so this is basically contradiction. This contradicts, implies contradiction to the fact, experimental. Okay, fact that for real fluids not zero. So this implies, this is what is called D'Alembert's paradox. D'Alembert's paradox. This is called D'Alembert's paradox. Okay. So I just leave it here. Okay. So what is the next point? What is the next thing that you do? So the next thing that you do is you try to do uniform flow. I have a uniform flow from infinity ux. I add, what is that I add? Basically, I had a doublet. Doublet, you have a doublet. This is where a doublet, right? So this is what is a doublet, right? The doublet actually will give you this circular cylinder, circular thing. Inside is one flow, outside is flow is separated. Flow is a flow is whatever flow, uniform flow. It won't penetrate through this doublet. Doublet inside is one flow, outside this doublet is another flow. That's how. So that's the reason you ignore that doublet and finally make it as a solid cylinder, and you make sure that you put this doublet strength in such a way that this boundary condition is satisfied. U dot n cap equal to 0 on the circular cylinder. That's how you get this flow past circular cylinder, uniform cylinder, right? I mean uniform flow against the pass the circular cylinder. This is what you have seen just now. Now I am trying to include, this is at 0, right? So at 0, I'll also include point vertex. Vertex flow that you have now, it is also called point vertex because only one vertex, right? So point vertex at x 0, 0, xy equal to 0, 0. Then what will happen? You are actually allowing the rotation. Okay. So this is what is this one? This is actually this one. So which direction? So you take the negative. So this negative vertex. Okay. Orientation is a negative vertex. Okay. So vertex strength is negative or clockwise direction. And this vertex. When you add, you actually see a different phenomena happens here. So I'm trying to draw this together, that thing. Okay. So you will have if you actually do the calculations, you start. What is that actually? If you consider, you calculate your phi. What is your phi? Phi of r theta equal to, so what is the uniform flow? That is u times r cos theta. That is ux. You have a doublet that is same. So what is the doublet that you have? Lambda cos theta by r. This is what is a doublet. This is uniform flow. And then negative. So I want a negative thing, right? What is that negative that you want? Doublet, right? So what is that doublet? Doublet flow, vertex. Vertex flow, what is the negative vertex? With verticity being negative. What is that? With circulation being negative. So that means minus times gamma. I want minus gamma theta by 2 pi. Do you remember? K theta will give you basically vertex flow. K is positive, anti-clockwise vertex. This is the vertex you get. K theta. What is K theta? Phi equal to K theta will give you this one, this direction flow. If K is positive. Now I have taken minus gamma, where gamma is positive, circulation is positive. So minus sign will give me finally, this is opposite. So you have opposite kind of vertex flow. If you include inside, basically you are inside. See this whatever you do, you are only doing inside, right? Vertex flow here also you are adding only at 0, 0. You have a doublet as well as you superimpose this vertex, reverse vertex. So then this is what is your phi. With this, if you calculate u theta, okay. If gamma equal to 0, capital, the circulation equal to 0 is basically flow past the cylinder that you already studied. Now you are including the circulation. Basically, if you remove the doublet is actually rotating, no? So it's a model for rotating cylinder, rotating in a anti-clockwise direction, clockwise direction. Okay, so you have a cylinder rotating in a clockwise direction. Fine. So in that case, if you calculate u theta and look at the direction of the flow, and I'm not going to do it here. I'll try to do in a different context. So I'll just try to give you the picture. Okay. So you do all the calculations that you do. Finally, you will see that if you bring out those that what is that you do? You are at a stagnation point, or you look for those in order to satisfy the boundary condition on the surface of the sphere. So you end up getting you actually looking for the stagnation point. Okay. So stagnation points, if you look for, they won't be just opposite to each other, that at 0 to pi. Okay, so you'll have some equation that gives you finally, I'll try to draw it so that we'll try to do in this complex situation we'll do. complex flows, when we do the complex flows, we'll try to do this one. So this is what you will have. Okay. So basically earlier you have, these are the two stagnation point. If you include your gamma you increase. Okay. Certain gamma values, your stagnation point will come to here. These are your stagnation points. So yes, as you increase, if lambda equal to 0 corresponds to these stagnation points, these two that you have already seen. If lambda equal to positive, you start increasing, slowly move towards to this side, and where at certain point it becomes here also. Okay, so the stagnation points are these. So what exactly happening? So this goes like this. This flow is going like this. Okay. So this is how it goes. Passing through the stagnation point, you have, these are your streamlines. This is how it looks if your stagnation points are here. You increase your gamma, this circulation strength of that rotation. Then what will happen? These two stagnation points at some point will become here. In that case, the figure will be looking like this. These are the stagnation point. So it goes like this. So this is how it looks. The flow looks like this. Okay, in this direction. These are your stagnation point. Streamlines passing through the stagnation point. Inside, anyway, you don't care, right? So this is how it looks. Now what happens? This is for gamma, certain gamma equal, gamma positive value, something. Okay, certain value. Now, why if I further increase, what will happen is, you can actually see, not now, but we will try to do later on, and when you do the complex flows. That is, there are the this is, here also you can do. See, we are not doing here because it's anyway we are going to do the introduce that complex potential, and we'll try to, basically what we are trying to do is we add phi and psi. Complex analysis, right? Complex variables you studied, right? Phi plus I times psi. That means potential function plus I times stream function will give you, basically automatically they satisfy Laplace equation. It becomes complex analytic function. So once you have the analytic function, those Cauchy-Riemann equations, basically you have a derivative, so you'll have a corresponding flow. Okay, so that potential, that is called potential. If you identify that potential, and you can calculate its derivative, so we'll do that. While when we are doing that, we again will do this source, sink, all these basic flows, and then combination of them, flow pass cylinder. Now flow pass the cylinder that is rotating, all those things we do there. I plan to do that way. So there also, if this is too much, you don't worry. So this is actually going in this direction. Okay, you have a rotating cylinder in this direction, but that is why with the circulation being gamma positive. So at one point of time, what happens is that you have the cylinder, and your thing will be somewhere here. Okay, you will have, it may have one stagnation point just comes out, one may be inside. So this is how it goes. This looks, in that case, this is the flow. It looks like this. Okay, this is your stagnation point. And this is how this gamma, this is the circulating cylinder, this with the higher gamma. Okay, so this is how it goes, and you start increasing. So let us say gamma goes to infinity. This is the case, the stagnation point both may go inside, then there is no flow. So this we will see, I will do in the complex flows. Okay, so we will not write here. So these are all these three type of things we can do here also, but lot of calculations based on this phi and psi. See, phi and psi. See, basically here also we are working with this phi, taking this gamma positive. Okay, so whatever may be the gamma positive is still your forces. If you calculate, it is going to be same. Okay, so forces will be different. With gamma equal to 0, you have seen that forces are 0. So when gamma is positive, you actually see, because of these flows, you see this symmetry is lost, right? Flow symmetry is lost, but flow is symmetric only in the left and right side. but not top and bottom. Top and bottom will give you this lift force. So lift force is non-zero. In this case, lift is non-zero, drag is still zero. Okay, so because you are dealing with potential flows, here also lift is non-zero, drag is still zero. So these things you will see while doing the complex analytic ways also you can do. Okay, so here also similar situation. So do you understand? So what we are doing right now is we have considered only solutions of the Laplace equation. That means del square phi equal to zero solutions you consider. You look at its and then based on that you calculate your UR component, U theta component. That basically UV components. You try to see the flow and its direction. That's all you are doing. Now you take the basic flows based on those calculations, based on those solutions. You try to superpose them because it's a linear equation. You can take the two such solutions and superpose and see, try to see new flows. So in that way you model this flow path cylinder, and also you can include the cylinder which is moving, rotating in a opposite way. So negative rotation we have taken because circulation we have taken negative, because if it is rotating anti-clockwise, from left side, if you allow the uniform flow, then you will see that lift force acting in the y direction. That's basically towards a lift force. Otherwise, nothing will happen. So it's going to go. The lift force is going to be in the down stress. It's like a depression kind of thing. Okay. So lift is aircrafts. You want this to happen. The rotation should be anti-clockwise cylinder, so that the lift force it goes up. Otherwise, it goes down. That is the only difference. This figure, whatever you are seeing now, this figure you try to rotate, you reverse it. Uh, okay, just ulta palta if you do, that's what will happen. So in that case, uh, so whatever that stagnation point will be above the cylinder, and so that all the lift will be only going in the negative y direction. Okay. So I think for you, I think just to understand this is enough as a first course. Okay. So when I come there tomorrow, what I do is on Monday, I'll try to start complex flows. So what is that complex flows that I do is basically, I want to define what is velocity potential. Okay. Complex potential Fz equal to phi plus I psi. So here itself you choose your phi psi for your sink flow or source flow. You get a source potential here for this, but you don't know. The problem is this when you combine it, you can understand, you can see it, you can see. So you can finally identify my f of z for all these basic flows, some in terms of log z, 1 by z, z power n, or like all these things. Okay, so these are the things you identify for each of the flow that you have already done. Instead of remembering those solutions of Laplace equation, you identify basically here, and then you see there is a way to use your mathematical knowledge of finding the solution. Dou df by dz, df by dz is its solution, right? So that will give you UR component and U theta component relation. Okay, actually something like this you will get. So based on that, you can get back your UR and U theta. So we will learn that to complex variable technique, how to get those complex potential flows for all the flows that you have considered so far. Okay, so this is what is my plan. Once you do this, at the end of the day, you can use whatever you are doing, whatever I'm talking about, you can do it in that context. That context, this context, both are same. Okay, instead of working with P alone, there you are including phi plus psi, you calculate and try to put it so that you start with that complex flow and try to get your flow direction, flow pattern. Okay, this is what I'm planning to do. So is there any question that you have? I can answer.
No, sir.
Have you understood the theme of what I am planning to do?
Yes, sir. Yes, sir.
So tomorrow I am going to repeat the same. So those whoever see, if I hope you understood the whatever I have done so far. If you are not understood, still all those basic flows I can do it through phi plus I psi. See, I'm only using phi. I try to do U or U theta component, or only through I psi also you can do. Psi you cannot do because we're dealing with the irrotational force, that is potential flows, right? So finally you need involving phi, right? So even with psi, once you know psi, you can calculate phi, right?
Yes, sir.
So suppose you know psi, I can get u and v. Once you know uv, I know what is my phi. Same thing. So you work with phi and try to get the flow. That is what we have done so far, and all the combinations that we have done. And the nonlinearity is coming to picture through the momentum equation by Bernoulli equation, because we are dealing only with the non-viscous fluids so far. So your equations are basically mass conservation and boundary conditions will give you, what is that? Laplace equation with the boundary conditions. So that is a linear equation, linear PDE you are solving. So you can superimpose all the solutions. That's what you have done. And finally, where is the nonlinearity? Nonlinearity is still there through the Bernoulli equation, which is the momentum equation in this case for the non-viscous inviscid fluids. But still, because there is some lack of some viscosity is still required. The motivation coming through a paradox, that is called when you calculate the forces on the flow past the cylinder, what you expect in reality is you don't see in this case. Okay, so that gives the motivation that those lift and drag forces won't be, in reality won't be zero, but here it is zero. That is the D'Alembert's paradox. And while doing the okay, so that's what say similar thing we will try to do by adding by considering phi plus I psi both together. So in that case, what exactly my complex potential? You can easily identify different situations like source, sink, vertex, and then combination, doublet, source and sink combination will give you doublet, doublet plus uniform. That's basically doublet plus uniform. What is that you got? Flow pass cylinder. Again, doublet plus uniform plus doublet plus rotation. That vertex flow, if you consider, just now we have seen, that is where we will try to do what kind of potential flow, complex potential force, complex potential function. We will get this lift force actually non-zero. Okay, you can actually calculate for this kind of where flow symmetry is lost, all the figures that you have seen just now, right? So you can easily see if you want to see. These kind of figures where the flow symmetry is lost, only top to bottom symmetry is lost. So that's why lift is non-zero. So these in general, for any general body, we can actually calculate lift and drag forces. Okay, that is what is your actually Blasius theorem. So those things we do, and then we'll close this potential flow problems. Okay, so when I come there, hopefully I'll try to finish in 4 hours. 4 hours may not be. Sometimes on Monday I'm given for 2 to 3 hours. In fact, 3 hours. We'll try to maximum based on our energy. We'll try to minimize. Slowly we'll learn and we'll try to interact with you guys. And I try to explain you 1 or 2 flows. Same way you try to do the calculation, so you can easily. We'll try to finish whatever up to here. I mean the last one with rotating cylinder. That also we can do, but we are not doing here. Here also we could have done, but instead we will do there. Okay, so both are same. So I'll try to finish this, and then there is some and one more thing that I should have done earlier, but I forgot, and that is called minimum energy theorem. So what is that minimum energy theorem? Kelvin's minimum energy theorem. What is this that tells you? Minimum kinetic energy. You can easily feel, no, this one. What is this tells you? For irrotational flows, there is no rotations in the fluid. For irrotational flow, what do you expect? There is no kinematic energy, right? Kinetic energy will be there, but you want it to be minimum, right? For suppose you consider a fluid flow with rotation, okay, with rotations, and there is a flow without rotation, no rotations. Which one will have more kinematic energy? This one, right?
Yes, sir.
This will have less. That is what exactly Kelvin's minimum kinematic theorem. Okay. So, I think I wrote it here. So I'll just try to. So that one I'll try to. Maybe I'll do it tomorrow. Okay. It is just a small theorem kind of thing. So we'll try to do. Okay. So I'll try to share this one. So we'll not do this. We could have done this here also for different by considering this one. This being your solution. Okay, this being your potential function. What is your potential function? Phi of r theta as a solutions. This is one solution, this is another solution, three combinations. When you make these three combinations, what you get is this. You could have done this. You calculate UR, U theta and try to look for these flows. Of course, there is a way to do looking for stagnation points again. Through stagnation points, UR equal to 0, U theta equal to 0 for different R, different theta, you can calculate. Same thing we will try to do by imposing complex potential. That's what I'm trying to say. Okay. So I think I'll stop here and I will see you in person directly on Monday. Okay. Two,
Okay, sir.
2 to 5 they said, but let us. I think we'll have maximum 2 to 4 at least, 2 hours at least, or 1.5 hour. We'll meet and try to initiate those complex flows and try to explain you this. Okay. Same thing, whatever you have done. Okay. So, and this is one thing. One more thing I want to point out. Okay. So maybe there itself tomorrow else I can do. I could have done here now. See, whatever you have done is only circular cylinder, right? That's what is the motivation. Circular cylinder, and you are using r and theta, right? Polar coordinates you are using, right? R and
Yes,
theta.
sir.
This is circular cylinder, right? Now I want circular what is this? Circular sphere. What do you do? If I want flow past circular sphere, flow past sphere, right? So what do you do? I will use spherical coordinates. Not no. I can use still cylindrical coordinates r and z. Okay, theta is removed. How do you remove this one? What do you call this one? This is called axisymmetric. Axisymmetric flows, right? Two-dimensional flow, right? This is a two-dimensional flow, axisymmetric, irrotational. Axisymmetric irrotational flow. Through that, you can actually derive the flow past uniform flow past circular sphere. It's we studied only this one. We need not study this one, but I try to introduce if time permits. But that is same as simple way. Okay, you can also work out the similar way, calculating all these UR, UZ component, and finally looking to see how it looks like that. Okay. So anyway, I'll see you on next class on Monday directly. Okay. So
Okay, sir.
I'll meet you all guys in person. Okay.
Okay.
So I'll
Okay.
share you
Thank
this again, this modified lecture 24 with you. Okay.
Okay, sir.
Yeah.
Okay. Thank you, sir.
Yeah. Bye.